All right, welcome to the third video for Mathematics 0110 lesson on graphing with calculus. This is another example where we're given some hints. We're given a function, ln of x squared plus 4, and we're told what its first and second derivatives are in simplified form. And we're given another hint too. It says that ln of 4 is approximately equal to 1.4 and ln of 8 is approximately equal to 2. Because we may need that information when we make our sketch, and if this was to be done without a calculator, you would definitely want this type of data to make your picture. Because no one knows what on earth ln 4 means. Like, what is it? Is it 2? No. Is it 1? No. It's in between. Because 4 is larger than e, but smaller than e squared. Okay. Part A, find where f of x is increasing and where f of x is decreasing. This is a property of the first derivative. So I'm going to use the first derivative, set first derivative to 0. We get 2x over x squared plus 4 is equal to 0. We also have to check where does it not exist. So this derivative doesn't exist whenever the bottom is 0, which never happens. We have x squared, which is positive, plus 4, which is positive. No matter what you plug in for x, you can't get a 0 in the denominator. So there's no solution that comes from f prime dne. We do, however, have a solution here. 2x is equal to 0 times x squared plus 4. So 2x is equal to 0. We get one solution, x is equal to 0. That tells us we have to cut our number line. Let's go back to original function and think about domain. We know that we can't plug a negative number into a log function. However, that doesn't mean that whenever you see a log, your domain is 0 to infinity with 0 not included. This particular log function has the x squared. So if you plug a negative number in, squaring it turns it positive. So something positive plus 4. The smallest the argument of this function can be is 4, and that's going to happen if x is 0. And 4 is in the domain of ln. You can plug 4 in, like the question right here tells you can plug 4 in, it's 1.4. Actually, you can plug in anything to the right of 0 into a log function. Anyway, so the ability to plug in negative numbers due to the x being squared means that our domain goes from minus infinity to positive infinity. We can cut the number line up at 0. I'm going to choose two test values. I'm going to pick -1 and +1. And then plug those test values into the derivative. So f prime at -1. We have 2 times -1 over 1 plus 4, so over 5. We get something negative. So it's decreasing inside the first region. From minus infinity to 0. Now we choose the second test value and plug it in to the first derivative. F prime of +1. We're going to have 2 times +1 over 5, which is positive. That means it's increasing in the second region. Increasing on the interval from 0 to infinity. Okay, so that's the first part done. Now we go to the second part. Determine the xy coordinates of any local max and min. Looking at the picture, we can see that it goes down and goes back up. So we have a local minimum there. Local min at x equals 0. The y value is the original function at 0, which is the ln of 0 squared plus 4, which is the ln of 4, which is approximately 1.4. So local min at 0, ln 4. we make the sketch, we'll need the decimal. And there's no max. Part C, find the intervals where the function's concave up and concave down. That's a property of the second derivative, so I'm going to set f double prime equal to 0. So negative 2 times x minus 2 times x plus 2 over x squared plus 4 all squared equals 0. We cross multiply. So negative 2 times x minus 2 times x plus 2 is equal to 0 times x squared plus 4 all squared. 0 times anything is 0, so I have negative 2 times x minus 2 times x plus 2 equals 0. And we get two solutions from that. We get x is 2, on the first bracket being 0, and x is minus 2, on the second bracket being 0. Okay, and there's no spot where the second derivative doesn't exist because the bottom can't be 0. We have x squared plus 4, must be positive. You can't get a negative number from x squared. You're adding a positive number to that, so definitely not 0 in the denominator. We're going to cut our number line at those two locations. And I'm worried about running out of space. 1 from minus infinity to infinity. We're cutting our number line at negative 2 and positive 2. We have 3 regions. We need 3 test values. So I'll pick negative 3 for the first region. I'll pick 0 for the second region, and I'll pick positive 3 for the third region. And if you felt like it, you could do negative 10, 1, and positive 10. The outcome will be the same. And I'll use green for the middle one, just so it's easier to track later on when you're looking at the notes. Okay, and we're going to do the same thing we've always done. We're going to plug our test values into the piece that we use to obtain these test values, and that's the second derivative. F double prime at negative 3. So we have negative 2 times, so negative 5 times negative 1, all divided by something positive. We have 3 negatives multiplied together, divided by positive, so negative times negative times negative, we're going to get a negative. And that means the function's concave down this first region. From minus infinity to minus 2. Now we have a second test value, f double prime at 0. So that's going to be negative 2 times negative 2 times positive 2, divided by something positive, and that's going to be overall positive. That means it's concave up in the second region. From negative 2 to 2. And we have one more test value at positive 3. So negative 2 times 1 times 5 over something positive, we get something negative. So that means decrease, or concave down. In the third region, from 2 to infinity. Okay. Next part. I'm going to draw a barrier there just to separate part C from part D. Okay. From the diagram, we see that the function is switching its concavity from down to up at negative 2 and from up to down at positive 2. So we have POI at x equals -2. Y is f of -2, which is the ln of 4 plus 4, which is the ln of 8. And x equals +2. The y value is f of +2, which is the ln of 4 plus 4, which is also ln of 8. So to summarize, we have POI at -2, ln 8 and +2, ln 8. And I can't remember the decimal. Oh, the decimal is there. It's approximately equal to 2. We'll use that when we make our picture, the decimalization. Okay, that's it for part D. Oh, that's the same question. That's the same question with more space. Interesting. All right, part E, determine the vertical and horizontal asymptotes. So for a log function, a vertical asymptote, ln of f of x, or I'll call it g of x, so I don't reuse f, ln of g of x has a vertical asymptote when g of x goes to 0 plus. And, well, I won't say and. What is g of x? G of x is x squared plus 4. And it never goes to 0 plus for any x. The smallest this gets is 4. It cannot go to 0 from the right. It doesn't go to 0 at all. So it cannot have a vertical asymptote. If the question said x squared minus 4, then we would have a situation with two vertical asymptotes. A vertical asymptote at x equals 2 and a vertical asymptote at x equals -2. We don't have that, so we don't have a vertical asymptote. Horizontal asymptotes. These are more straightforward. They come from limits. Limit as x approaches infinity of the function, ln of x squared plus 4. That's the ln of infinity, which is infinity. So not a number, so no horizontal asymptotes either. No vertical asymptotes, no horizontal asymptotes. Okay, now we can make our sketch, the last part, put all the pieces together. So we have a min at 0, ln 4, so 0, 1.4, and 2 points of inflection, one at -2 ln 8, one at +2 ln 8. So min at 0, ln 4, so 0, 1.4. Vertical asymptotes at -2, 2, approximately, or it's not, points of inflection rather. There's a POI there and then a POI there. No maxima, no asymptotes. Now we need the increasing, decreasing, and concave up and concave down information. So from the previous, we have down, up. So it was decreasing until we hit 0, and then increasing afterwards. And then for the concavity, we had concave down, up, down, and breaking at -2 and 2. So down concavity over here, down concavity over here, up concavity in the middle, and that will help us connect our dots. So the first connection is I'll make between the first POI and the minimum. It's decreasing and concave up. So decreasing and concave up. Okay, in the next region, we have increasing and concave up. Okay, now we need what's happening outside of these special points. So I'll start with the right-hand side. It's increasing and concave down, so it has this shape. And the last region, it is decreasing and concave down. So decreasing, concave down. Well, I don't need that little arrow thing. It's not wrong to draw it, but these aren't directed graphs. There you have it. That's what the sketch looks like. Now I'm going to erase this little bit here. And I'll erase this little bit here because it's going to cause confusion. Anyone checking the notes later, and erase that there. Okay. Just going to keep the part that's actually a sketch. Okay, and there's one more example. We'll save that for a separate video.